Hello everyone. Alright, today I want to do it fast. So let's see if we can get it done in half an hour. And I think it'll be challenging to do this, but we'll see. I mean, I have some idea, so we can try it, but not sure if it's gonna work. But anyway, let's try this one. This one looks fresh. Fresco. I don't think I've done this before. You're given two integer arrays, nums1 and nums2. In the order, right? Okay, we write the integers of nums1, nums2. On separate horizontal lines. The line we draw does not intersect. The line we draw does not intersect any other connecting non-horizontal line. Note that a connecting line cannot intersect even at the endpoints. That is, each number can only belong to one connecting line. Return the maximum number of connecting lines we can draw in this way. That is a very interesting problem. 1 for 2, 1 2 4, so we have 2. We cannot draw the third one because the line from will intersect the line from. That is true. Okay, let's just example this. Okay, so we have what? We have 2 5 1 2 5 10 5 2 1 10 5 2 1 5 2. Ooh. And it has to be interesting. Wait, they're not necessarily the same, right? The lengths are not necessarily the same. Oof, the line not necessarily. So what will we have? We can do 5 5. Oh, 1 1. Nah, I feel like this is DP. This has to be DP. Come on, otherwise we have to go through all possible ways. For example, we can say DP IJ is the max uncrossed line. Not sure, just try it. Uncrossed line between, let's say, nums1 all the way to I, or let's say I plus 1, and nums2 all the way to j plus 1, right? Okay, so if I know that, can we do, what is dp I plus 1j? I mean, probably not the best way to ask. Is like what if I know all the dp previously? Now what's dpij? Right? That's the better way to ask. So, you know, we might be able to use this as an example. But just write it out. Right, we have 1 4 2 1 2 4, right? And we're gonna have a 3 by 3. 0 1 2 0 1 2. Okay, so 0 0 is gonna be this and this, right? 1 1 2 2. 0 0 is all the way to 0. So this we can say, okay, then I have 1. And then we can say, I can do this, I say is nums1. And this is nums2, right? So nums1, this is nums1. This is nums2. Okay, so I want nums1 to be 0. Nums2 is 1. Nums1 is 0, nums2 is this. And for this, the maximum is going to be 1, right? So we say, because 1 and 2 is not the same, so it will have to be default to the previous one. See, now we start to see things. But in this case, it's all going to be 1 because we have this. Now it will be interesting. Nums 1, we're going to do second one. So nums 1 is going to be here, right? So it's this and this, right? So we definitely compare these two are not the same. If these two are not the same, then we need to compare this, all right? And that's 1. Here is interesting. These two are not the same. So if they are not the same, like 4 and 2 are not the same, right? They're not the same, so we cannot draw 1. So the maximum shall be diagonal-wise, right? It shall be either 1, 0, this, or 0, 1. 1, 0, 0, so the maximum of this will be 1. Then these two are the same, right? If they're the same, then we shall count it, and then we do diagonal to 0, 1. So that should be 2. Yeah, so this is the same as, what's that thing? Longest common substring. Longest common subsequence. Okay, the last one is 2, 0. Right, this and this, they're not the same, so we need to do, so this is actually is going to be, Jesus. That cat is crazy. All right, this is going to be 1. So this is going to be the same, right? 2 and 1, they're the same. So with diagonal-wise, it'll be 2. And the last one is going to be, this is not the same. So it's going to be a maximum of this or this. So that will be 2. So the answer is 2. Now, to facilitate the computation, I think we shall make it a little bit bigger, right? 1 larger. So this is just a, that's what I think, a variation of the common LCS, longest common subsequence. So we're going to code it as such and see if it works. It shall work. Okay, mn len nums 1, len nums 2, right? And then we say dp is going to be, ooh, that's an interesting question. Can we do a simplified dp? Yes, we can. Yes, we can. Because all we need to know is this one and this one, right? Which means we'll need 1 row, and that shall be, oh, we go directly to 1 ddp, dude. And we do n plus 1, right? We do n plus 1. Okay, so now what do? We will say for I in range m, okay? For j in range n, dp, if nums I is equal to nums j, right? Then dpj shall equal to, it's a diagonal. What is the diagonal? Oh, diagonal. Diagonal. I don't think we can do diagonal. We cannot do diagonal. We need 2. We need 2. That's fine. That's fine. So we have dp. We have a temp. Okay, temp will be the same thing. So if they're the same, then that should be 1 plus that should be temp, right? Temp is the dp, 1 plus dp, dp is I minus 1, so j minus 1. Pay attention. we do it one more. So this has to plus 1. Okay, plus 1. So this has to be minus 1 plus 1. I like to make it clear. Minus 1 plus 1. Okay, that's that. Else temp j plus 1 shall equal to maximum dp j plus 1, which is up, and to the left is going to be temp j plus 1 minus 1. All right, and then blah blah blah. Once we're done, dp equals temp, and now we do it again, and at the end we'll return the last one. All right, let's take a look. Should be 2. This should be 3. And this shall be 2 again. Nums 1, nums 2, nums 1, nums 2. Max. Nums 1, nums 2. Nums 1 and 2. Okay, looks to be right. You wanna try edge case? Sure. Okay, this is pretty edge case. Okay, that shall do. Yep. It's the same, exactly the same. 1035. This is a variation. This is exactly the same algo as longest common subsequence. But if you think about it, it is the longest common subsequence. You don't want crossing. Yeah, if you don't want crossing, then you should get a maximum of this, right? And then you don't have crossing. If they're not equal, then yeah, it's the same thing. It is the same. Okay, check the solution. Recursive, iterative. Yep. Space optimization. They gotta have 2. Come on. Yeah, we have to. Okay, so this is done. We have some time left. Let's take a look at this one. All right, so let's go back. We drew something yesterday, and I want to just draw it again. So here's the idea, okay? So we have, this is the timeline, right? We have 1, 2, 3, 4, 5. We have 2 to 3. We have 4 to 5. And we have 1 to 5, okay? And then, this meeting here. And then we want to know, right? We want to know at the key points, right? Key point, how many people are together, how many tasks are together. And the goal is like greedy. We want to process the starting, we want to process the key time where we have the most overlapping tasks. So here we have task 2, right? And it's task 2, and we start. So we have task 2, and we start at 1. So that's that. Here we have task 0 and 2, right? And we start at 2. Now this is tricky because we are including, it's inclusive, so we have to count. So this is also an important point, and this point is again 0 and 2, and we start at 3, right? And this point is 0, not 0, 1 and 2. We start at 4, and this is 1 and 2 when we start at 5. Okay, so we throw all this into a priority queue, and the condition is the number of overlapping, number of I have to call parallel, right? Number of parallel tasks. Bigger the better, right? Bigger the better. And the second, we have a second, is the number of seconds that we can take advantage of, right? So the number of the length, right? The task length. Longer the better, which means we can take care of more of the tasks. So that means we want to check the length of this, and we want to check, because the task length, right? Task length is dependent on your starting position and the current task length. And here we have task 0, task length is 1. 1 task length is 1. Task 2 task length is 2, right? So in this case, when you add this, right, the condition is number of parallels 1, and the task length, we start from 1, okay? Then we can check tasks 2, so we have length is 2, right? So at this position, do we have 2 left? So we have to check. We check to see that this one can last until 5, right? So it's gonna be the minimum, right? Because I'm at 1, so the total, the maximum time that I can do for this task is 5 seconds. 1, 2, 3, 4, 5, right? And I need 2. So this one I have 2 seconds. And we say, okay, that's that. So this, the length of the task is 2. So this will rank higher than this one. And we start at 2. Now we need to compare 0 and 2. Okay? So for 0, we start at 2. We end at 3. So 0 has 2 seconds maximum we can do. And 0 has 1 second. Right, 1 second is its current time. So for this, the max task length is 1 second, right? So this one, so this is length is 1, task is 2. This one, length is 1, length is 2, task is 1. And this is interesting. Okay? Again, 0 and 2, so length is 2, but the task, we have a task, we add 3, okay? We add 3. And we say, for task 0, we are at 3. What's the total number of seconds remaining? We can do, that's 1 second, right? We're at 3, we can do 3. 3 minus 3 plus 1, so it's 1 second. And it's 1 second as well. And for task number 2, we're adding a 5. So the total seconds allowable for task 2 is 5 minus 3 plus 1, which is 3 seconds. And it's 2, right? So that's 2. So max for this one's 2, max for this is 1. So overall, is 1 second. So this is 1 as well. So these two actually is the same, right? These two is the same. Okay, here is length is 2, task is, we start at 4, right? Start at 4, so task is 1, right? Again, 1, because task 1 has only 1. Task 2 allowable is 4 to 5, it's 2 seconds, right? And it has 2 seconds, so the max is going to be 2, so we're going to do 1. This one, length is 2, and task is going to be 1. Again, task 1 has 1. Task 2, we had 5. It's also 1, even though it's 2, so it's 1. So, based on this, I think just randomly, I mean, all these tasks can just randomly pick one. Right? Well, we can say, let's say we pick, let's pick a weird one. Right? Let's pick a weird one. If we pick a weird one, and we will, wait, do we have to do this according to the time? That is a good question. I think we have to execute it according to the time, right? So then, holy crap, then we have to also check the starting time. Then it's actually more interesting. Starting time. Then we have to go with starting time. Yeah, that actually makes things a bit easier. Than this one does not exist. We don't need to consider this. Right? It doesn't matter. Oh, hold on. Hold on. Are you saying that, the starting time, right? Because these are the ranges. Yeah, I think time has to go from small to large. Now we have an issue with this method, because if I have another task that's like here, then that task has to run by itself, right? We cannot run this task. We cannot say, okay, I want to run this one first. Now what do we do? Well, we have to run the task started with smallest, right? It doesn't necessarily be first, but we need to check to see if we have an opportunity to run it again. If we have an opportunity to run it again, how do we check? So for each task, I need to know if it can share with another task. If it cannot share with another task, then it has to run by itself, right? That makes sense, right? That makes sense. So we go from small to large. Oh God. We go from small to large. How do you know something share? Well, I mean, these means they share, right? So you can do this. And then you can check each one. We can say, okay, this is 2, so we can say the share. Who does 0 share with? Right? Who does 1 share with, and who does 2 share with? So the first one is 2 is by itself, so nobody's sharing with 2 at the moment. And now 0 and 2 is here. So we say, okay, 0 will share with 2 at position 2. 2 will share with 0 at position 2, right? And then now what do you count of this? You say 0 is shared with 2 at position 3. At position 3. At position 3. Let's not consider this for now. See how we get. And then we can say, okay, 1 share with position 2. Share task 2 at position 4. Okay. Let's see if this works. And 2 share with 1 at position 4. Okay, so we go through this. We go through the task list, and if there is any that's by itself, so we have to do it on its own, and anything else that always share with others, so we can try, right? And when we share, and we'll have more or less, right? Therefore, aren't we still doing this? Yeah, I think we're still doing this. We're still doing this. And we say we're starting from, hold a second. I think this still works, right? We just use the earliest time. If you share, we use the earliest time. But what if we have multiple share? Yeah, I can see if we have, like, say 3 tasks share at a later start time, and then they go through a longer. Yeah. Oh, it doesn't matter, right? It doesn't matter. Because when we do the priority queue, we can do it in any order. It does not matter. It does not. No, it does not matter. No, it does not matter. Because we'll keep track of this. We'll keep track of this. Right? This is what we keep track of, so we know which one has not been finished yet. So now we go back to the earlier idea. I think this t still needs. We still need a t, the task, the maximum task length, and this is not necessary. Right? We don't need to do this. This is fine. Okay. So we have priority queue. Then we get, let's say we do 0 and 2 starting from 2, right? And then when we get that, we know the time is going to take, right? We know the time is going to take to the maximum task time that will take. So this is task is 1, okay? So after we handle this 1, we check 0 is done, right? And 2 has 1 left. So we push 2 and 3 because I done second 2, so we move on to second 3. So we push this to the priority queue again. Okay, so now our time is 1. And then we pop whatever, right? Whatever we pop out. And if like 0 pop out again, then we say no, because 0 is already we've done it already. So this one will be eliminated. If it shows up, it will be eliminated. So next, let's say 1, 2, and 4 shows up. Okay, 1, 2, and 4 shows up. And the max is 1, so I do it. When I do it, 1 is gone. 2 is gone. Right? 2 is gone. So this one is, we don't put anything in. So now we have 2 seconds. And then we're basically done. And the next one come up will be this, but we can check or they're all gone. Actually, we can just check this, right? This is empty, so we just escape, right? We just escape. This is actually quite an interesting idea, right? You want to give it a shot? You want to... I mean, I said half an hour. It's already half an hour. It's quite complex. All right, it's quite complex. So we need heap queue, right? So I need a function to know. Hold on, does heap queue has a key? No, they don't have a key. Merge has key. And largest has key. These all have keys. But push doesn't have a key. Damn it. Yeah, what are we gonna do? These have key. But heap push doesn't have key. Huh. Then how are you gonna handle the... Oh. I mean, it could just be a tuple, right? I mean, I think we can do a very long tuple. We can put the length at the front, the time at the second, and then we put these two. Let's try. Let's try. I'm not sure. Import heap queue. Okay. So I can say A equals. Let's try this. 1, 2. Let's try 3. Length is 1. Let's say the largest is gonna be 2, but we want a. It's not gonna be min heap, so I want the largest length, the largest task length. Okay, and then I want to have 1, 2, and I have 2, something like this, right? And then we have -2, -3, and 0, 1, 1. Doesn't matter what it is. And the last one, let's say -2 and -2, 0, 2, 3. All right, so that's that. So let's try heap queue dot heapify A. I expect -2, -3 to be at the front. It is. It is. So what if the first two are equal? If the first two are equal, because this will not be equal, so I need to put this one in the front. Because if I say heap q dot heap push a, if I want to push, let's say -2, -3, okay, they're equal, and I do 0, 0, doesn't matter, and I do 2, this shall be error. Oh, it does not error. I use whatever it does to compare these two, but I don't want it. I want to compare, I want the smallest to go earlier. Although it doesn't really matter too much, but okay. Tuple. We can use a tuple. Cool. So what do we do? Okay, we need to sort tasks. Okay, so we sort it first. And then we need to read along. And then we need a heap, right? Okay. And we need to read along for s start and duration. sed in tasks. Okay. All right, sed in, maybe we just say sorted tasks. Okay, sed in sorted tasks. What do we do now? Oh, we have, this is start, and every time we have a start, we need to add something. We also need, damn it, we also need overlap. This can be set. Okay. Okay, so we need to add, right? We need to add the start to the overlap. So every time it's start, we can say overlap.add start. Okay. Overlap the dot add start. But it also no line sweep. Huh. I should go one by one. At this position, wait, hold on. How do you do line sweep? You minus, right? You minus. Nah, that's not what we want. What we want is go one by one. When we hit it, in this position, and we hit a certain position. Yeah, that's what we want. That's what we want. So I need another structure to know at any point what is starts and ends. Okay, starts, and call it default dict. Okay, let's call it default dict of a list. That's the start. And ends also default dict list. Okay, then we say, this one maybe later, we say starts s dot append. Oh, we need also enumerate. Oh man, this is start as I, right? And e dot append I. We also need another thing, is task duration, right? Task duals, default dict int, and task duals, this task doesn't need to be int, it's just gonna be a dictionary, it's fine. This shall be d. Okay, all right, so we go through the tasks. Fine, we go through the tasks, we get all this, and then we need to go through the start and end. Okay, so for t in range 1 to 2000, okay, and then we have overlap. It's going to be a set. Okay, so we say if t is in starts, then we need to add all the starts into it, right? We add all the starts into it. Then we say, maybe we can do, maybe instead of, that's fine. We can just say for task in starts t, or we can just say overlap equals overlap dot union starts t. Then we just do this as a set, right? And this is what we do add. This is what we do add. Then we just union, right? If t in starts, then we get all the starts, and then, right? So this is a start, and we get whatever what if it's an end? What if it's both a start and an end? Dude, man. Okay, let's handle end first then. If t in ends, if t is in ends, we need to get whatever's overlap, right? We need to get whatever overlap into the heap. Okay, whatever overlap into the heap, and then we need to remove all of these from overlap. I think I can just do this plus, right? Set can do plus. I think it can. A plus B. Cannot. We can do minus. Dude, you can do minus. You can now do yeah, union. That's fine. So t in ends. So for everything in overlap, so these are inside the overlap. So for each one, we need to check, right? We need to check the minimum longest task length at the moment. How do we check? How do we acquire that? Well, at the current moment, I think this deserves a function. Right, let's do a function for this. Let's do a function. So what function are you thinking about? Well, I'm thinking about def get max min task length. Okay, so we're gonna get a tasks, and then we're gonna return an integer. All right, so for each task, we also need to have the start, right? We need to have a start. So for each, then we don't need to sort it. I mean, we shouldn't sort it anyway. Then for each task, right? For each task, I will check. So for task in tasks, okay? So I check the and, right? And just S and E, and shall equal to tasks. Oh my god, I have tasks already. Underscore tasks. Okay, so that should be tasks, task 1. That's the end, right? That's the end. Now, allowed shall equal to end minus start plus 1. This is total allowed time. And then I also have the current, right? The current task durations. Okay, the current task durations. Then we need the minimum of the task durations task and the allowed, the smaller of the two. And we want to know the maximum mean task length. So everyone has a task length, right? So to get the minimum task length, actually, it's the minimum task length. Everyone has a task length. We want to get the minimum task length among all the tasks, because we don't want to overdo it. So rest I can do math.inf, that's fine. And then we can say the result equal to the minimum of result and this. And when we're done, we'll return res. Okay, so if that's the case, right, then we need to put this whole group into the heap. Then we say heap q.heap push. Heap. Okay, we're going to push a tuple inside. So we start with len overlap negative. What's next? Len overlap. Next is the task length. So get min task length overlap, right? So that's that. And this has to be negative as well, because we want the longest to go in the front. And after that, we want the t, that's actually the starting position. And the last, we want a list of overlap, whatever the overlap is. So we will push this, and after we push this, right, that overlap equals overlap minus and t, because these are no longer in the overlap, but we have to push it first and then take them out. Okay, so that's if t is in ends. And when we've done this, then we check if it's in starts. All right, if it's in, then we will union them, and then we do the same thing, right? We do exact same thing. We union them, so we get a new bunch of stuff, and then we'll push this again, right? We'll push this again. Oh my. Okay, so that's the effort. I'm gonna stop right here. It's gonna take a while, and I'm pretty sure this is not the optimal solution, but at least I need to get this to work, okay? And if it doesn't work, then we check the hints. All right, I'll stop right here, which I think we, if we take a look at the heap, right? We can actually take a look at the heap. Let's take a look at the heap before we end today. Just make sure that everything looks right. Okay. We have tasks. Find minimum time. Tasks. Find minimum time. Argument S. Oh Lord, I forgot S. S is just T. S is just T. Okay, that's the first one. Does that make sense? We have 1, 2, 3, 4, 5. One, two, three. 1, 2, 3, 4, 5. Yeah. So we start with length 2, 0 to 2. Right? 0 to 2. 2 and 1. And then 1 to 2. 4. 2 and 1. 0 to 2. 3. 2 and 1. 1 to 4, 1 to 2, 5. And the first one, 1 and 2. Yeah. It looks fine. Right? So we have the heap. Now we all need to do is, let's say, while task durations, right? While task durations. Then we just get the first one out, right? Now we say, what do we need? We need a task length. We don't need this. So say this task length. Actually, we should say D, the duration, and T is the time, and this is the tasks. Okay, underscore tasks equals heap q dot heap pop heap, right? And then we need to make sure that we only handle the ones that's still in the task duration, right? And we know this is the maximum we can do at the current moment. Well, honestly, that's not true because it depends on what task duration says at the moment, right? So we go through the tasks, check the task duration. So this is not needed either, right? This is not needed either. So we go through the tasks, check this, right? If, what if have to be everybody is in this in order to make it work. Otherwise, we have to recompute and push it back into the heap. T is the starting time. That's fine. So we can say for task in tasks. So we can say new tasks. Okay. New task is equal to this. If task is in task durations. Okay, new task equal to this. If task in task durations, then we keep the task. Okay. We say if len new task is not equal to len tasks, then we're going to push it back in, right? We're going to push it back in. Now when we push back in, we shall say heap q dot heap push heap and this thing, right? We need to push it back in. But of course, this is going to be new tasks This is going to be new tasks. The current starting time. Yeah, current starting time. And then we can compute again, right? We can compute again what is needed. And then we will do this. And then this is just going to be new tasks. If that, if not new tasks, then continue, right? That means we don't have anything left. If we have something left, if it's not equal to, then we do this. Else is they're equal, right? They're equal, then we can execute. We can execute the task, right? We execute the task. So we can say the duration shall equal to, we need to recompute it, right? Recompute the duration, and then for task is the maximum that we can go. So for task in list task durations dot keys, right? Task durations task minus equal to D. If not task, that means we've done it, right? Del task durations task. Right? Once we're done, we need to have a result equal to 0, right? So this D will take it, right? We'll take it, rest plus equal to D. Now we need to put whatever is not. So we have to have a new task as well here. Oh, we already have a new task. Dude. If not equal to, then equal to, then we use task. We can actually use new tasks, it's fine. Remaining task, rem tasks, okay? So task if not, which means it's 0, else, so we have something left, then rem task dot append task. So right? Once we're done, rest added, then we say if we have remaining tasks, then we have to push this into the heap again. Right? We need to push this, and this is going to be remain task. Remain task. Now that's not T, right? That's not T, because we from T we did D, right? From T we move forward D times. So the current is going to be, the current time is going to be T plus D minus 1. That's our new time. T plus D minus 1. And this is going to be remain tasks, right? Because I'm at 2. If I do 1 second, oh, I think just plus 1. Hold on. If I'm at 2 and I do 2 seconds, so we do 2 and 3, right? So I'm actually I consume 2, I consume 3. That's 2 seconds. So I'm now at 4. So it's actually not minus 1, just T plus D. Right, if I remain task, we add it to it. And then we'll go back up, right? And then we check, and then we do. And at the end, when everything's done, we'll return res. Oh my god. Is this right? Oh, no, it's not. All right, now we have to wait until tomorrow. Yeah, it's lots of moving pieces. Lots of moving pieces. Yep, we check tomorrow. I'll see you guys tomorrow. Adios.